Good morning, good afternoon, good evening, and welcome to a science post. This one is on high temperature superconductivity. In 1987, a Nobel Prize was awarded for the discovery of materials that could behave as superconductors at a temperature which is far above absolute zero. Typically, superconductivity only occurs when one cools a substance, like mercury, down to around 3 degrees Kelvin with liquid helium. I think that what happens looks a bit like the video I have in the blog post linked below of cornstarch and water on a speaker. It's a non-Newtonian fluid. One sees this, in terms of mercury, it sort of becomes one with the vibrations contained in empty space. The vibrations that make up the 2.7 degree Kelvin quantum vacuum. As of 2019, the material with the highest accepted superconducting temperature is highly pressurized lanthanum decahydride, whose transition temperature is 250 Kelvin at an elevated 250 gigapascal pressure. At atmospheric pressure, the record is still held by cuprates, which have demonstrated superconductivity at temperatures as high as 138 degrees Kelvin. There is presently no good explanation for why we see superconducting behavior at high temperatures for certain materials. At least I did not enjoy the Wikipedia explanation given in terms of Cooper pairs, so I've decided to make my own, because I believe that it's possible to describe things in regular words without resorting to codified jargon. In superconducting materials, no electric field can exist. No charges or electrons can exist. The electromotive force equals 0, equals IR. Inductance times resistivity. Current times resistivity. It's been a while. There is no resistance, so there can be any current. Room temperature superconductivity only happens because the extreme pressurization creates an artificially colder vacuum around the conductor. Colder, you might ask? I thought pressure made things warmer. Pressure makes air molecules move faster, but we aren't talking about air molecules here. We are talking about waves in empty space. A substance with a temperature and an energy density. It's full of vibrational motion, but perhaps no matter or rotational motion. Some call this the quantum vacuum. Some call it the noise floor of free space. Some call it the cosmic microwave background radiation. I'll just call it empty space. It helps to think in terms of mirror images, something that British people are particularly good at because of how they do everything backwards from the rest of the world. With matter and empty space as two sides of a looking glass, empty space looks cold to us, but we look cold to empty space. When we increase the pressure of empty space, it will feel hotter, but look colder to us. And when the vacuum around an object gets colder, the object is going to behave colder, and exhibit superconducting behavior. Essentially, the pressure creates a false vacuum around the conductor. If this doesn't connect intuitively, just think of how coals in a furnace will glow red when you blow on them. Contrariwise, the hotter the fire, the stronger the draft, and a strong draft is colder than the air that is still. When we put pressure on the fire, the coals glow red, while the surrounding space becomes colder. It seems that pressure caused things in the coal to speed up, while things in the surrounding space slowed down. At this point, you might remember that relativity tells us that things that move faster act like they are colder and spaced further apart because they have themselves length contracted. Stepping away from the language of temperature and expressing the same concept in the equivalent language of motion, we see that when matter gets out of the way, current can flow quickly, and intense pressure causes matter to move or vibrate faster and concentrate, length contract, in small spaces within an object, causing the object to behave as a superconductor. An electrostatically equivalent explanation of length contraction can be given in terms of figurative spatial expansion, as in the 1937 superconductivity theory of Landau expansion. This is similar to how the universe only appears to expand as when the space around an object sitting in sand acts like it expands when the sand begins to vibrate. This explains the high temperature superconductivity of certain materials under high pressure, but it doesn't really explain cuprates, quasi-two-dimensional materials that demonstrate superconductivity at atmospheric pressures, but at a temperature of 100 Kelvin. This is cold, but well above absolute zero. What is quasi-two-dimensionality, you might ask? It's quite simple, really. Just take a piece of paper and randomly poke holes in it until it is half holes and half paper. Then make a stack of those papers and you have a quasi-two-dimensional substance. How light or energy propagates through these quasi-two-dimensional objects simply cannot be described by mean field theory, no matter how creative you are with how you define the fields. They require something more like a real space renormalization group method, which predicts magnetic hotspots, or monopoles, on each sheet with an extremely intense local field. These hotspots suck all of the charge out of the sheet, leaving behind the necessary conditions for superconductivity, where no electric field can exist. No charges or electrons can exist. The electromotive force is equal to 0, as in the current times the resistance. There is no resistance, so there can be any current. Now, I only studied a quasi-two-dimensional material, or quasi-one-dimensional, I guess, when I wrote an undergraduate thesis on semi-continuous metal dielectric thin films. And it was quite easy to construct a mathematical model of how the fields on those films behave. That was a real space renormalization group method, and I suppose it's probably much more complicated to construct the math to describe those objects in 3 dimensions, but I bet somebody knows how to do it. Oftentimes, problems like this one become difficult to solve because they carry around a ton of theoretical baggage. And when you reduce them to their base elements, they are eminently solvable. When people ask for money while selling dreams of long-distance transport of electricity using room temperature superconductivity, it is important to note that magnetic hotspots, or these magnetic monopoles, in these materials, they tend to break the material down so that it can't act as a superconductor forever. Likewise, dreams of flying cars with magnetic levitation due to eddy currents, they can be done with superconducting and with normal conducting objects. It just requires a lot of energy to create those conditions. Mother Nature doesn't provide a free lunch when it comes to basic physics. So be careful whenever somebody's asking you to write a check for a fantastic new idea. People have been having these fantastic ideas for the past couple hundred years, and they've been pretty thoroughly checked out. On the other hand, maybe I am just thinking too narrowly, and lightning is an example of room temperature superconductivity that happens when the voltage potential is high enough. Putting lightning in a bottle is another matter, though. They've been trying to do that with fusion experiments, and they've been making tiny pulses of lightning in a bottle in particle accelerators since forever, but they consume far more power than they transport. If I were to try to imagine a perfect imaginary superconductor, I'd make it self-repairing. Magnetic monopoles would be born, they would reproduce themselves, and they would die in a semi-organic negative entropy system. Negative entropy systems consume energy, though. After all, we are negative entropy systems. Are we powered by room temperature superconductivity? I think I will conclude this with a song that is about heat, which I think is what you really have to understand. The relativity of heat and hot and cold. That's what you have to understand room temperature superconductivity. So perhaps this song will inspire you or not. You'd be so nice to come home to. You'd be so nice by the fire, while the breeze on high sang a lullaby. You'd be all that I could desire, under stars chilled by the winter, under an August moon burning above. You'd be so nice, you'd be paradise to come home to and love. Under stars chilled by the winter, under an August moon burning above. You'd be so nice, you'd be paradise to come home to and love. Thank you for watching this video, and please tune in for the next one. I also invite you to take a look at my novels. They were an enlightening journey for me, and I hope that they would be a similarly enjoyable experience for you. Until next time.